Okay, so for this screencast, we're going to do something called quadratic spline. So if you watch my other video, I did one on linear splines, and I'm going to step through linear splines very quickly here. So I've already have this coded. So I have clear, CLC, close all. I have x is negative 10 to 10. I throw a transpose in here, so it's a column vector. Y is sine 5x. I do a figure. I set the color to white, the axes, the font size to 18. I plot XY with blue stars here, and then I do a grid and a hold on. So I'm gonna hit play here, and I get my figure here. So it doesn't really look like anything's going on. So if I was looking at this data, I'd be like, okay, if I was given this data, I wouldn't know what it means. So if I step through here, and let's put this guy here. So if I step through here, I'm gonna put a debug point here, and I'm just gonna hit continue. Every time I go through, I draw a line here. So I did this in another video. So basically what I'm doing is I'm just connecting the lines with linear lines. So I compute the slope here between two endpoints. I make a x coordinate that goes from one endpoint to the other, and then I plot it in a green line. So every time I hit continue, I connect the lines here. And then I'm going to step through here. So basically this linear spline is just connecting all of the dots individually. So it looks like I kind of have some semblance of what's going on, but it's still very choppy, and it would be nice if I could kind of smooth that out. And that's where quadratic splines come in. So the code for quadratic splines is fairly extensive, so I actually went ahead and wrote it ahead of time. So I'm going to step through this code one by one. But basically, you have three separate conditions for quadratic splines. The first condition is that the spline connecting from one endpoint to the other and the spline to its adjacent neighbor, the value in between each spline needs to be the same. And so in this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 interior spline points, and that will give me 18 unique equations. Now, what I have here is the length of n is 21. The number of splines I have is 20. So the number of lines that is connecting is 20. So then what I do is I create this matrix called H0, which is a 38 by 60, which essentially says the number of columns is 60 because each spline has three coefficients, A, B, and C, and then I have 20 splines, so 20 times 3 is 60. I have 60 unknowns that I have to solve for. Now, when I say that each individual spline needs to be equal to each other, what I actually mean is it needs to be equal to the value here, y0. So what I end up getting is I get 2n minus 2, so n again is 20, so that's 40, so I get 38 unique equations that govern the fact that each interior point needs to be the same. So I'm going to step through here, and essentially I get this big H0 matrix, which is my 38 equations that say that my interior points of my splines need to be the same. And then I make the H1 matrix, and the reason why I call H0 H0 is because it means that the value of the functions need to be the same across interior points. H1 means the value of the first derivative needs to be equal at the interior points. So if you see here in H0 I have x squared terms and x, and that's because I have ax squared plus bx plus c. So down here when I take the derivative of that, I get 2x plus b, and then the c drops off, and that's why I have 2x terms and negative 2x terms here. So when I step through this, notice that the first derivative term, I have them equal to each other. Now the reason why I don't have 2n minus 1 equations here is because I don't actually know what the first derivative is. So I just set them equal to each other. So instead of getting 38 equations, I get n minus 1, or 19 equations. So I essentially set them equal, each interior first derivative equal to each other, and that gives me an extra 19 equations. The final piece that I use is this is the final condition, is that the spline must pass through this point, and it must pass through this point. And so that gives me two extra equations. So when I create this matrix, I have HE is a 2 by 60. So again, I get two extra equations here. So I have ax squared plus bx plus c, and then ax squared plus bx plus c, and here I have the first point, and then I have the last point, which is essentially saying that it's the first point and the last point that I'm trying to set equal to. Now what I do is I combine all of my matrices together, and I get a 59 by 60, which means I have 59 equations and 60 unknowns. So the way to solve that is you assume that A1 is 0. So you assume this spline here is just bx plus c. So you actually assume that this first spline is linear. So we'll see that when we run through. Now k is what the solution is. So I made a k0 matrix here. So up here I have a k0 matrix. So basically when I was creating the h0 matrix and I was saying that the two splines were equal to each other, I also wanted them not only to be equal to each other, but I wanted it to actually be equal to the measured data that I had, y, which is why I have a k0 here. Then I just have zeros everywhere else because the first derivative are supposed to be equal to each other. So if I subtract one from the other, I get 0. And then finally, the first point must be equal to the first y-coordinate, and then the last point must be equal to the last y-coordinate. So I generate my k matrix there, and then I make the assumption that A1 is 0, so that makes the first spline linear, and then I get H is a 59 by 59. So now I have 59 equations and 59 unknowns. So then I just do inverse of H times K, and I get my 59 coefficients. Now in order to get my 60 coefficients back, remember I assumed that A1 was 0, so to get out my A coefficients, I just take my coefficients from 1 to n minus 1, and then I get 20 coefficients. And look, if you notice, the value of A0, or A1 is 0, and then A1 is 0, and A2 is 1.2. And then I keep stepping forward, I get my B coefficients, I step forward again, I get my C coefficients, and then now I can do exactly what I did for the linear splines, except I do it for quadratic splines. So I make my x coordinate go from my first point to my last point with 10 points, and then I just do my quadratic spline equation, ax squared plus bx plus c, and then I plot that in red. So as I step through here, you'll see a spline added. So again, here is my first linear spline that we assumed, and then here's my second spline, and notice here that rather than just going linear between them, I make this nice quadratic. And then every time I step through here, I add an extra quadratic spline. And at the end of the day, and I think I add a legend here, at the end of the day you get this nice curve. And so basically we started with our blue stars, which was our measured data, which had made no sense whatsoever, and then we connected the dots with linear splines, and we didn't really like that very much. And then now we have quadratic splines, and now we have a nice smooth curve here. So basically quadratic splines will sort of smooth out your curve a lot better. And then there's obviously cubic splines as well, but obviously the math for that is way more intensive, because not only are your interior points equal and your first derivative equal, but your second derivative is now equal. So essentially you have an H0, an H1, and an H2 matrix, and then you have to invert all that. But it's still totally doable and within the realm of something possible. All right, I'm going to scroll through this code real quick so you can pause and take a look at here. So here's line 1 through 28. And then here is line 29 through 56, and then finally 56 through 83, and then 83 through 87. All right, good luck.